Today we're going to talk about how light behaves. And the most basic fact about light is that light travels in straight lines, except when it doesn't. Now, the exceptions come when light interacts with matter. Um, but when it's traveling just in empty space, light travels in a straight line. The exceptions come when it interacts with something, and those exceptions are called reflection, refraction, scattering, diffraction, absorption, and dispersion. And what we're going to do now is we're just going to go through each one of these and explain what they are. So specular reflection, it refers to reflection off of a shiny object like a mirror or a smooth glass or smooth lake of a pond. In fact, speculum is the Latin word for mirror. So specular reflection means mirror-like reflection. As opposed to diffuse reflection off a rough surface like my shirt or the table or something. When talking about specular reflection, this is really the simplest equation, the simplest law of physics out there, is that if you have a ray of light, let's say it's a laser beam, and it's hitting a flat mirror, we're looking at this in cross-section, okay? So this laser beam hits a mirror and it bounces off. And the angle that it makes with the mirror over here is equal to the angle it makes over here. Now you're probably noticing that I'm not pointing at the indicated directions in the diagram because normally what we do, sorry for the pun, is we define the angle of incident relative to this dotted line, a geometrical line that's defined to be perpendicular to the mirror. So technically the angle of incidence is this angle. And the law of reflection is that that angle is equal to this angle. The light will bounce off so that that angle is equal to that angle. A little bit more complicated is refraction. So refraction is the change of direction of a light ray due to a change of its speed at the boundary between two media. Why does that happen? Let's clarify. First, I want you to consider this is an aerial photo taken like from a helicopter looking down on the beach in North Carolina. And you can see some waves. My question to you is, what directions are the waves moving? What direction are the waves moving as we look down on them from above? Just take a second, and hopefully you are thinking something along those lines, that they are moving in the direction of the black arrow. And I want to point out that that direction is perpendicular to the wave itself. The crest of the waves, the line of the waves, is perpendicular to the direction that the waves are moving. That's a key point for understanding how waves move. We call that arrow that indicates the direction of motion of the waves, we call it a ray. Back to the topic of refraction. So here we have some rays, and I know it doesn't make sense for me to point with my finger. We have a ray. Now what I've done here is, in the animation, it includes, these are called wave fronts. These are like the ripples, like you're looking down on those breaking waves coming into the beach. And so here are the waves coming into the beach, and they're traveling in a straight line until they hit this boundary. Now, let's say this boundary is a piece of glass. And, well, light travels at 3 times 10 to the 8 meters per second in space. But inside glass, it travels about 30% slower. So as you look at these wavefronts coming down, what part of the wavefront is going to hit first? It's going to be this side, which, if you think of this as, like a car coming towards the glass, it would be the right-hand side, although it's the kind of lower left on the diagram. But if you imagine a toy car driving towards the glass, from the perspective of the driver, it would be the right-hand side of the car that hits the glass first. And if you're driving a car and the right-hand side slows down compared to the left-hand side, you're going to turn to the right. The animation shows this wavefront, these ripples turning and lining up closer to the normal, which again is the dotted line. Here's a static diagram showing an incident ray here hitting a piece of glass. We're calling that theta 1. And when it goes into the glass, it bends so that theta 2, the angle from the normal inside the glass, is less than theta 1. Now, generally, if you have a light ray hitting a piece of glass, probably most of the light will go into the glass and through the glass, but you'll get some reflection off. That's this diagram is also showing a reflected ray coming off. Refraction is the bending of light, the turning of light rays when they go from one medium into another because they're changing their speed. Now, how do we use this? Lenses use refraction to focus light. So on the left here, we have a bunch of wavefronts. So these blue lines are like those waves at the beach, and we're in the helicopter looking down on the beach. And the red arrow is the ray, indicating the direction of motion of those wavefronts. And here's a piece of glass. Here's a piece of glass. It is convex. It is fat in the middle. And the wavefront in the middle here has to go through a thick piece of glass. Whereas at the top and the bottom of the diagram, the wavefronts there only have to go through a little bit of glass. So when the wavefront comes out of the lens, the middle lags behind because it was traveling slower, longer. So it lags behind the top and the bottom, the left, right, and left side and right side from the perspective of the light ray. What started as a flat or planar wavefront is now curved. And this is where the ray being perpendicular to the wavefront is crucial, because if the wavefront is curved, then, like it is here, then these rays must be converging. They're coming together. In your eye, you have the cornea of your eye and the lens of your eye together act as a system to converge light rays and to focus an image onto the retina of your eye, actually both your eyes. Cameras do the same thing. They have lenses. If it's a nice camera, they're glass. If it's a low-end camera, it'd be plastic. But the lenses focus light rays, converge them onto, well, an old camera would be photographic film. Obviously, most cameras these days are going to use a little electronic chip as the detector, not photographic film. Let me real quick, before we move on, just mention concave lenses are where it's thin in the middle and fat at the edges. And concave lenses cause light rays to diverge, to spread apart. Next topic is scattering. You can kind of think of scattering as reflection, but it's reflection off of small particles. Small particles. It doesn't follow the law of reflection. There are, furthermore, two different kinds of scattering. There's what's called Rayleigh scattering. And Rayleigh scattering is scattering from particles that are smaller, much smaller than the wavelength of the light. As you know, the wavelength of visible light is 400 to 700 nanometers. And a characteristic of Rayleigh scattering is that it is more efficient. It happens more for shorter wavelengths. In this photograph here, there's blue sky. The reason the sky is blue is because of Rayleigh scattering. Because the sunlight contains all the colors, Roy G. Biv, but what gets scattered the most is the blue end of the spectrum. And so the blue light gets scattered. The red light doesn't get scattered so much. It does ultimately when the sun is right on the horizon. You get red sunsets because then the sunlight is going through so much air that even the Rayleigh scattering of red light is noticeable. The other kind of scattering is called Mie scattering, and it is where the particles that are doing the scattering are larger than the wavelength of the light. And so if we have light coming in, Mie scattering tends to scatter the light in different directions, but preferentially in the forward direction, and it's not wavelength dependent. So again, back to this picture, we're looking at the sun. Around the sun, there is a large patch of sky that is not blue. It's white, and it's white from Mie scattered light from the sunlight that is scattered in the forward direction, all wavelengths, in a patch around the sun. Next is diffraction, and diffraction is the spreading out of light after going through a hole or past a barrier. Here are some waves that are moving from the left towards the right, propagating to the right, and there's a yellow wall that has a small hole in it. And so the waves go through the hole and they spread out. The reason they do that is, if you think about the hole, that's a pretty small hole. And the smaller the hole, the more the waves going through it are disturbing the water, kind of like if you just dropped a rock into a pond. If you drop a rock into a pond, it doesn't make wavefronts that are straight or planar, it makes concentric circles. So the smaller that hole is, the more the waves coming out of it will be circular as opposed to straight. Now, when I say small, the word small is actually meaningless. It has no meaning unless you compare to something. You can say smaller or small relative to something. And so in this case, small means compared to the wavelength of the light. So if the hole is comparable to the wavelength of the light, or smaller certainly, then you're going to get a lot of diffraction, and the smaller the hole, the more the light diffracts. Next is absorption, and absorption is the capture of light and conversion of its energy into other forms, usually heat. I'm sure you've been outside on a warm day and just turn your face up to the sun, feel the warmth. Your skin is absorbing the sunlight and warming up. We call compounds or materials that absorb light selectively, we call them pigments or dyes or filters. Now, some materials absorb light of all wavelengths, so we would call these either black or gray or neutral, but some are selective, and so we would call this a colored dye or paint or a color filter. So for instance, here's a picture of my family. So in the life preserver here, it is yellow. Why is it yellow? Because it is not absorbing yellow light. A lot of the red light, the green light, probably like most of the blue light is being absorbed, but the one color that's being reflected from the sunlight, the one color that's being reflected most efficiently is the yellow, and the other colors are being absorbed. Blue shirt, these are reflecting the blue, absorbing the other colors. These inner tubes are absorbing all the colors of the light equally, so we call that black or gray. Next comes dispersion. Dispersion is the spreading out of light, the sorting, if you will, of light into an order according to their wavelength. And this produces a spectrum. So here is the spectrum of a light bulb. And it is what we call a continuous spectrum. All the colors, Roy G. Biv there. If we were to graph that brightness, this vertical axis is brightness, and this horizontal axis is the pixel value across here, you would get this wide swath. Not all the colors are equally bright, but nonetheless you have, all the colors of comparable brightness. So that's called a continuous spectrum. Now, some spectra, when you separate the light, disperse the light into a spectrum, you don't get this continuous, smooth Roy G. Biv. You get this a pattern of bright lines with dark gaps. The gap is that there is no light of this color, but there is a lot of light of this particular wavelength, this particular color. Not any light of this color or this color, but light waves of these particular colors. And on the graph, that looks like, peaks are the bright lines. So this line here is this one here. These two lines right here are these two lines in the graph. So how is it that you separate light into its different colors? There are two basic ways, a prism or a diffraction grating. A prism works because of refraction. And I got to admit that I lied to you a little bit earlier. When talking about refraction, we said that refraction happens because the light slows down when it goes from air or vacuum into, say, glass. And that's true. That's true. But the different colors slow down different amounts. Not much, just a little bit. But the blue light, or the blue end of the spectrum, slows down a little bit more than the red end of the spectrum. If you have white light that enters the prism from the left, the rays are going to bend. But how much they bend depends on their color. The blue-violet rays are going to bend a little bit more, just a little bit, than the red rays. And also when they come out of the prism, they'll bend different amounts. The other way is what's called a diffraction grating. And a diffraction grating is a surface of glass, typically, that has microscopic either slits or scratches on its surface. Light going through the glass or maybe reflecting off the glass. There are transmission gratings where the light goes through the glass, and there are reflection gratings where the light reflects off. Depending on how much of the slits or the scratches, depending on the spacing of those, the waves constructively interfere in only certain directions. And those directions depend on the wavelength. Unlike a prism, where it's the blue light that bends the most, for a diffraction grating, it's the red light that bends the most. Next is the Doppler effect. The Doppler effect is the change in observed wavelength, or frequency, if you want to think of it that way, of a wave due to either the motion of the observer or the source, or perhaps both. Now, I'm sure you've heard this for the case of sound. Sound, you've been standing by a street and a police car goes by, or a fire truck, and it's so the frequency, or race cars, that sound. Now, so I'm not talking about the sound getting quieter. Say, as the race car approaches, it gets louder. As it goes away, it gets quieter. So I'm talking about the change in the pitch, the change in the frequency or the wavelength of the sound. So, and so that would be like the sound of a race car going by. The question is why it does that. And so here's an animation just showing waves coming from a source that is stationary. Circular wavefronts traveling out in all directions. But now, here are the wavefronts for a source of sound that is moving. And it's moving to the right, and you can see that the wavelength is the distance from one wavefront to the next wavefront. So to the right of the moving dot, the wavefronts are more closely spaced. The wavelength is less than it is to the left. And since the wavelengths are less, the frequency has to be higher. And so in front of the moving dot, if this were sound, you would hear a higher frequency to the right. To the left in the diagram, you would be hearing a lower frequency, a lower pitch, if it were sound. Now, if it's light, then to the left, you're going to hear the light's going to be shifted, to the right, in front of the moving dot. The wavelengths are less, and we call that a blue shift. And to the left of the moving dot, the wavelengths are longer, and we call that a red shift. There's an equation that governs the Doppler effect, and it's a simple equation. V over c. V is the speed of the moving object relative to you. Okay, so it could be that the object is moving, it could be that you're moving, it could be both. But there's a speed relative to you, either towards you or away from you, and that's v. C is the speed of light, and that ratio is delta lambda over lambda. So lambda is the normal wavelength of the light, as if the object weren't moving. And delta lambda, remember delta is always a change of something. So it's the difference between the wavelength that you observe and the wavelength that was emitted, the normal wavelength. So the faster the speed, the bigger the delta L. And we can use this, by measuring delta L, we can use it to measure the speed of objects. This is just recapping what I was just saying, that the blue shift, if the source is coming towards you, the observer, the wavelength will be shorter, meaning And astronomers use blue to really refer to that end of the spectrum, even though violet's the very end, towards the blue, meaning shorter wavelength. And a redshift means towards longer wavelengths. A little aside here, we've talked about the universe a little bit. We've talked about the fact that the universe is expanding. Well, how is it that we know that the universe is expanding? Is because every galaxy in the sky, except for just a couple of exceptions, every galaxy in the universe is moving away from us. And, you know, if there were aliens on some other galaxy, they would see us moving away from them, and all galaxies moving away. So space is expanding. Everything is moving away from everything else. That was our first clue way back in the 1920s that the universe is expanding, and had a beginning that we now call the Big Bang. A quick question. Let's say that a particular emission line, a particular feature in the spectrum of a galaxy is observed at 606 nanometers, whereas in a lab on the Earth, the same emission line has a wavelength of 600 nanometers. So my question to you is that galaxy moving towards us, away from us, or not moving at all? Take a moment, hit pause if you need to think. And it's moving away. So it was observed at a longer wavelength that is redder than normal. And so that must be because the galaxy is moving away from us. So now the question is, how fast is the galaxy moving away from us? Here are your choices. Again, pause, do any math you need to do, come back. Okay, the answer is 3,000 kilometers per second. Delta lambda is 6 nanometers. Remember, delta lambda is the change in the wavelength from its normal wavelength. So 606 minus 600 gives you 6 nanometers. 6 nanometers divided by the normal wavelength, which is 600 nanometers. So 6 out of 600, or 1%. 1%. 0.01 is the ratio. And so the galaxy must be moving at 1% the speed of light. The speed of light is 300,000 kilometers per second, and so it must be 3,000 kilometers per second, 1% of the speed of light, that the galaxy is moving away from us. That was our quick tour of the behaviors exhibited by light.